Hey guys, welcome back to another episode of Simuleos. Today, what we're going to be doing is working on the Huffman algorithm one more time. So, we made a lot of progress yesterday. I unfortunately did not make as much progress on the determined video as I wanted to yesterday afternoon. I had intended to work on it for pretty much the entire afternoon, but I kind of got sidetracked with one thing or another thing. Sorry about that, but that's okay. I think I should be able to finish up all the visualizations today, get all the audio recorded. Then I should be able to edit it over this upcoming week, hopefully getting it out on Sunday, because that's, my goal. But the thing is, I do have to teach a skill pill this upcoming weekend, so it might be that I'm not able to finish everything on time. So we'll see. This upcoming YouTube video might be a little bit late. Hey guys, everyone, thanks for coming in. Okay, so as always, let's go ahead and get started by opening up Zernal and talking about what the Huffman algorithm is and why it's cool. Then we're going to talk about what we're doing today, which is basically fixing up everything that we kind of broke yesterday and hoping that it works. I've got a feeling that there's going to be some issues here and there, but we'll see how far we get. Okay, so what are we going to do? Let's do the following. Let's say, oops, sorry about that, I hit the microphone. Let's say we have a couple letters, I don't know, A, B, C, D, E, and we want to turn this into a couple of bits. Of course, bits are easier to transmit than letters, and we want to change them into bits in such a way that we have an optimal number of bits at the end. Now, in this case, you might think, okay, well, the frequency of finding each of these guys is about the same, so they all have about 20% chance to come in. So we have A as 0.2, B as 0.2, C 0.2, D as 0.2, and E as 0.2. And then what we do for the Huffman algorithm is we add up the two lowest valued numbers all the time. These guys add together to 0.4. These guys add together to 0.4. Then I suppose these guys add together to 0.4 or 0.6. And I feel like I'm doing something a little bit weird here, but that's okay. And then these guys add together to be 1. Then we add these 1, 0, 1, 0, 1, 0, 1, 0, and we count backwards. So A is going to be 1, 1, B is going to be 1, 0, 1, C is going to be 1, 0, 0, D is going to be 0, 1, and E is going to be, let me see, 0, 0. And this way we have an optimal storage of the bits because they're all equally as likely to come in. This will work just fine. Now, I guess that's about it. So this means A, B, C, D, E would be stored as 1, 1 for A, 1, 0, 1 for B, 1, 0, 0 for C, 0, 1 for D, and 0, 0 for E. And there you go, you have your bits. Now obviously the reason this is optimal is because if we have one number that is somehow, or one letter that is somehow way more frequent, it comes in all the time, then that particular letter, according to this tree, would not be added until like the very last step. And because of that, it makes it so that particular letter is encoded with fewer bits, so that the number of bits that we use in the end is optimal. For example, using the same example we had before, if A came in with a frequency of 0.6, B came in with a frequency of 0.1, D came in with a frequency of 0.1, I missed C, C came in with a frequency of 0.1, and E came in with a frequency of 0.1. Add these guys together, 0.2, 0.2, add these guys together, 0.4, and then add these guys together, 1.0. 1, 0, 1, 0, 1, 0, 1, 0, A, B, C, D, E. Then A is 1, B is 0, 1, 1, C is 0, 0, 1, D is 0, 1, 0, and E is 0, 0, 0. And in this way, A has 1 bit, but B, C, D, and E all have 3 bits. And so if we stored all of these bits together, and made a whole bunch of A's, this would be incredibly efficient. But if we have more B's, C, D's, or E's than A's, then this is an inefficient scheme. And we'll get into the fact, or we'll get into later, like next week sometime, about how to make the Huffman algorithm dynamic and efficient for any string that you read in. And that's pretty cool. That's something that we'll go into later. So what are we doing today? Well, today we're finishing up the visualization of simple Huffman trees, I think. We've been working on this for a while and I keep running into issues. In particular, we need to get the correct XY placement for all of the individual nodes, external nodes, and internal nodes. Now, when I say node, I basically mean if we draw this tree a little bit differently, let's take that same tree we drew before. We'd have A was 0.7, A, then we'd have B, C, D, and E. Down here was 0.1, 0.1, 0.1, 0.1. We'd add these guys together, these guys together, these guys together, these guys together, and we get 1. And so the nodes are each of these guys down here, and all of these internal nodes in here. Now for now, we're just gonna try to find a good representation scheme for this. After that, we're gonna kind of work to see a number. We're going to work on a number of different things to make it a little bit easier to understand. So hopefully this will be super visually appealing. It'll be super understandable and stuff like that. So let's go, I guess, one step at a time. So let me go ahead and oops, sorry about that. Let me go ahead and get started. So let's go ahead and pop this over to the next desktop. I don't know why, for some reason these past few streams I've been incredibly tired for them, and I don't know how to fix that. So let's go ahead and cd into projects, Simuleos Huffman. Same thing over here, cd projects, Simuleos Huffman. Okay, let me grab a quick sip of water real quick. And then we'll go ahead and get started. Hey, iCare, thanks for coming in. I'm gonna put this down here so it's easier to get to, because my back is killing me right now. Okay, so what do we have so far? Let's go and open up Mirage, frames, animation.gif. Now this is significantly different than what we had before. The X positions are kind of weird. Let's see, the Y positions are kind of weird. We gotta fix a lot of different things. So one thing that I wrote down a couple of different things that we need to fix on. Let's go and open up the code and see what we need to do. So let's go into VI Huffman visualization.cpp. Okay, we modified a good bit of stuff yesterday. So what I need to do down here in notes, in draw tree, we have some nodes that are being overwritten. So you'll note that some of these positions here, let's just scroll down. Here's 1, 2, 3, 4, 5, 6. But see this guy right here, if we go up a couple of, oh, sorry about that. This guy right here was a C. Now it's being overwritten by a D. And then I think that D is being overwritten by something else. So we have a couple of different dots that are being overwritten. So the X positions and Y positions are not being set correctly. So that's one thing that I need to work on. Draw internal still needs to be completed, and that's what I'm going to be working on first. And then we need to check the Y positions in the draw tree command. Okay, so let's go down and start by working on the draw internal command. Okay, give it a second to load. Good. So what do we need to do? Well, we already have all of the, let me see here. We already have all of the X and Y positions of all the internal nodes. Now we just have to actually draw them. So, draw layers. That's not what we need. We need draw internal. Okay, if we go down to main, you'll see that I have draw internal commented out. Let's comment back in, and let's go down to draw internal. 1 second. Gosh darn it, draw internal. There we go. Okay, so what do? With this guy, I have kind of generated a couple of different positions to use. So in this case, we're not going to generate the positions here. We already have them generated before in the draw tree command. So now we just have to actually draw the internal nodes. So let's go ahead and do that. Because I have this this file copied elsewhere, I'm going to go ahead and delete some of these lines that we don't need anymore. dy we don't need, double angle. Do we need angle? Let me think. Yes, we're still going to need angle, and we're still going to need number of lines. probably. Okay, so node 1, node 2, node parent. While regenerating nodes that size is greater than 1, here's what we do. We say node 1 equals regenerating nodes top, and then we pop it out. And we say node 2 is regenerating nodes top, and we pop that out. Now we say regenerating nodes pop, and we say node parent is equal to new node. Okay, that's exactly what we want to do. Now here's the thing. This is actually a little bit different. So what I did last time is I had only external nodes, and I basically recreated the Huffman tree in order to draw these nodes. And the reason I want to do that is so that, how do I put this? Is so that when we, one second. Is so that when we, wait, let me think here. So that when we redraw the tree, it is redrawn in the way that people would typically draw Huffman trees, which makes it a little bit more intuitive as to what's going on. So we have these guys here. We don't need to set, we no longer need node parent here. Let me think. Actually, wait. Node top, node top. Oh, wait a minute. I'm thinking about this incorrectly, I think. How do we calculate the Y position before? We calculated the Y position based on some sort of level diagram, right? Let me think. So we have all the positions of the... Hey, Flood from Now here. You started streaming exactly when it's my bedtime. Sorry about that, man. I know how that feels. I go to bed kind of early, so I totally get that. What do I have up here? What's all this that's commented out? Oh, draw external. I can probably get rid of this function entirely because I no longer use it. I know I'm deleting a lot of lines here, but again, because we have a copy outside of this, it's okay. Okay. The other thing we need to do, gosh darn it, my eye is killing me. The other thing we need to do, probably get rid of all these lines in here. Okay. So what we did before is we redrew the Huffman tree. So we did exactly what we did in the previous Huffman tree. We just started with external nodes and we drew all the internal nodes from there. However, in this case, we have all of the internal nodes. So what we might do is something a little bit different. We might do, one second, I think we already have all the left and right nodes already attached. So the one thing we don't have is node parent. So let me go through and let's see what we need to do. I would guess we would do this. So we're going to go through and we're going to say node 1 equals regenerating nodes top. And let me think. We should probably just, instead of doing it this way, do it another way. So we're going to go through and we're just going to ignore every solution that is at a an external node, and then we'll go from there. Let me see. Alan Forts. PHP isn't so great. Are you kidding me? When was the last time you saw a programming language with such an ability, stability, and performance? PHP puts the game and other in another level. We will be blessed if we ever see a programming language written with such passion and emotion again. Java breaks records, C# breaks records, PHP breaks the rules. You can keep your statistics. I prefer the magic. Well, Alan Forts, that's fine, except for the fact that we don't do any PHP on this channel, nor do we do any C# or Java, for that matter. So all of that argument was moot. But thanks for the comment anyway. I appreciate you coming in. Okay. So what do we do? Node 1, none of this matters. So here's what we're going to do. Instead of having a node 1, node 2, node parent, let's go through and remove all of these guys here. So we're going to say node, but I'm going to call this, what do we want to call it? We should call it like test node or temp node. I'm going to call it temp node. Temp node. Okay, so we're going to say temp node is this. Well, Alan Forts, you did what you needed to do. You started a bit of a discussion in chat. Okay. So temp node is equal to regenerated nodes top, regenerated nodes pop. And now what we're going to say is this. What do I want to do? Here. So if temp node, one second, node temp key. So if there is not a key, then we do this. So again, only the, how do I put it? Only the external nodes will have keys. So this is a way for us to say, are we on an internal or external node? I almost did Fortran commenting there. Are we in an internal node? On an internal node? Okay. So if temp key, then we are. Okay. So next, we don't need any of this node parent stuff for now. And let's see, what do we want? We have node 1. All this stuff looks like it's probably not worthwhile either. The only thing we need is this animate line stuff. So let's go down here. And let's animate the line. 1 second, here we are. Good. So what do we need here? We have animate current frame. Then we have time divided by number of lines. That's fine. We have the origin. Then we have 0. Ori 2. So how do we define Ori? Ori is going to be... Okay, so what's the 0 again? The 0 is, oh, the radius of the sphere that we're connecting to. Okay. So because we have this on different layers, we shouldn't have to worry so much about this anymore. But before, I was gonna have to worry about the radius of the different layers and stuff like that. Now we should be fine. So let me go up to animate line. And let's fix it up a little bit. So now we no longer need radius 1 or radius 2. Because we're going to assume that this is drawn on the appropriate layer. So let's remove radius 1 and radius 2. And let's go down here and fix up the function. So anytime we see radius 1 and radius 2, such as these guys in here, we no longer really need that anymore. So let's go ahead and remove these. So let me see. Ori X. Let me see. These guys don't look like they're necessary. Now let me see. Is there anything else that we have? Radius? No. Okay. So draw internal. Let's go ahead and remove the radius from the draw internal command. Let me see, radius. Looks like we use it here, but all these are going to be commented out in a bit. So let's go up to draw internal. Here, and again up here where we originally call it. Here, and let's remove the radius there. Oops, my bad. Okay, so let's go here, remove the radius. Now let's move up here. Let's see, draw external animate line. And let's remove the radius from here. And here. Now, what else do we need to do? Now, anytime we do animate line, we have to call it appropriately. Of course, I think it's only called in draw internal. Yes. Okay, so now we have to do draw internal. Internal. Here it is there. And now we have to remove the next. So it's after generated nodes, we have to remove this 10 here. Good. Okay, now going back to draw internal. Let's continue on. Okay, so here we are at draw internal. Okay, we need to animate the line. We have animation dot current frame, time, which is the amount of time we want to give it. Let's remove these 2 zeros here and there. Now we have to draw one of the lines. This line we'll just say is a left line, so we're just going to assume left line. Okay, so now we should probably do something. Let me go up to the top, write this, go up to the very top, and we have the struct position. Let's grab this struct position, and let's move it into another file. So let's go into vi huffman.h, and let's move it into this file here. Super easy to do. Now what we're going to do is we're going to move into, let me see, Huffman tree. What do I want? I want in each of the nodes, yes, so I want to change this double xy into a position xy, or into a position, and I'm going to call it Ori, which is the origin. So let's do position Ori, which is, again, the origin. Now, let's see. What we need to do now is go into huffman.h, huffmanvisualization.cbp, and I guess we'll just see if this runs. So let me look for dot x, origin.x, that's fair enough. Ori.x, ori.x, all these are ori.x's. Animate line, let's see, ori.x. Okay, we're gonna have to do this in something real quick. Where are we? Draw tree. this is probably where we need to fix it. So we have double X in draw tree, but what we should probably do is make it so this isn't just a draw. This isn't a double X anymore. Well, no, this is probably fine. Let's just change this to ori.x. Well, that was a 0, ori.x, and ori.y. Now I've got a feeling that I'm forgetting something, so I'm going to go through and fix this in just a second. So we position ori, but we don't need these guys anymore. We can just go ahead and draw grow circle with the origin. Now what else do we need? Ori.x. I think this should at least compile. Well, actually, wait. Draw internal is probably not going to compile. Let me go and fix that up. So here's what we're going to do. We are going to comment this out for now, and comment out draw internal up top. And then we're just going to pretend that it is working for now. We'll fix it in a second. I apologize for being so rusty or so dirty with my coding right now, but give it time, it'll get there. So now we have to go up to main, and let's comment out draw internal. I've got a feeling that this is going to not compile, so I kind of want to make sure that we give it the best shot we can for this to compile. Okay, we're going to do this, and of course, 1 second, that. Now let's go to, what do I need to do? I think make. Okay, and let's see where it breaks. It breaks at struct position, Huffman visualization. Let me see. That's because I didn't remove that. So let me go to 28. And let's remove the new struct position, which has already been defined. Okay, ori was not declared in this scope. Let me see. Visualization.cbp 343. Let me see. 343. What do I do here? I removed a couple lines. Grow circle ori. So this is going to be root pointing to ori. And now let's write this and let's make it. Ori.x was not declared in the scope 350. And what do we have? Okay, so this is going to be root pointing to, and again root pointing to. Okay, let's go ahead and write this. Make. And it looks like it's making something. Let's check the animation afterwards. Hopefully this will turn out okay. If not, we have a little bit of work to do. I'm going to go ahead and open up the blinds now. I like kind of having them open. It's, you know, I get to see the sunset while or the sunrise, I suppose, while coding. It's kind of neat. So mirage animation.gif. Looks like all the positions are the same as they were before, so nothing is inherently broken there. Let's keep going from there. Okay, so now we have draw tree. Let's go back to draw internal. Regenerate nodes, we need that one. What is all this has commented out again? Oh, this is a draw internal command. Okay, let's go here. And let me go up to the top. Draw internal. Here we are. Next. There. And last. Here. And there. Okay. If I click it again, we should get here, draw internal. Okay, so we have the animation of one line. Now let's animate another line. So we have Ori and Ori 2. And all we want to do is draw this from the following point. So we're going to say, what do we want? Temp node. We point to the left node. And then we say dot Ori. I think I have to point to Ori. Sorry about that. Point to Ori dot. Oh, just Ori. And then we do the same thing here. So let's see. Let's pop this down to the next line. Temp node. And then we do the same thing over here. So we say temp node. 1 second. And then we just point to Ori. Okay. Now we animate the line one more time. Except this time, we change the time at which we are animating it. So let's grab this guy. Put it here. And let's go ahead and remove some unnecessary spaces. So I believe there will be 8 of them. There we are. Let's add a couple here. There we go. So animation, animation, current frame, time. And what this is doing here is it's making it so we draw both lines at the same time. Then we say time. Let me see. Divide by num lines. What is this one going to be? 1 second, I'm looking here. Animation current frame. Oh, so this is setting the frame, and then that's setting the time. That's fine. Let's go and remove this 0 and this 0. And now what we need to do is basically call this guy here. So let's do temp node, except instead of left, it's going to be right dot ori. So this is going to be right. And this one's just going to be temp node dot ori. Okay, so this should be drawing everything to the appropriate node. I think the positions are wrong. I think I know why the positions are wrong. I think the algorithm we're using is not going to work here, but I'll get to that in just a second. I just want to see if we can get to the internal nodes, and then we'll go from there. So now we have the 2 lines being animated. At this point, I don't think we need anything more. So let's go ahead and get rid of these guys here. And now we're set. This massively cleaned up that function if it works. So now let's go over here and let's make it one more time. Good, I'm glad you're excited. So let me see, what do we have? It's because it's not temp, it is temp node. So where are we? Temp node. Okay, let's go ahead and write this. Go over here to make. Warning, angle is not used. That's fair enough. We can change that. Okay, so now let's take a look to see if this is actually doing what we want it to do. I've got a feeling it's not, but that's okay. So let's go to mirageanimation.gif, give it a second to do its thing, and it is drawing all of these guys correctly, but we clearly see now that there are some missing lines. Huh. Okay, so let's see, what do we need to do? We are drawing a whole bunch of lines. That's great. And it looks like we're missing a line at the very top. At least one line. So let's see. Let's kind of mix this around a little bit. So animate line. There's something here that's not right. Let me see. Let's try changing the number of lines to 40. Why not? This is just an arbitrary number. And let's see what happens. So we're going to go here. And we're going to do make. Hey Ivco, what's up? Okay, so the other thing we need to do is remove this angle because it's not used. Now, once this is drawn, let's see how bad it's breaking. Miriam, I would say you're missing points and that they are outside the image. Yep, that is what I would say too. But the other thing that I don't like here is if we draw all these guys together, we are missing the biggest point of all. So here, let's scroll down. Okay, so there's a couple things here. First, these lines are not being drawn at the same time. Okay, so you'll note that this guy, I'm actually making the animations myself with Cairo. Cairo is a graphics processor, or graphics, how do I put this? Graphics library, I guess is all it is. And we're going through and we have every individual frame set as a kind of Cairo specific term known as a context, which is a combination of all of the different basically layers in Cairo. So they have 3 layers. They have a source layer, which is a layer where you basically have all the paint. So that's like the color that you're drawing with. Then they have a mask layer, which is a layer that's kind of like a stencil. So if you were like spray painting or, you know, doing graffiti, you would have a stencil and you'd kind of spray paint it. And that's kind of the idea there. And then of course they have the surface, which is what you paint to. So a mixture of all these guys together gives you a context. And what we've done is we have a vector of contexts put all together into this one struct called frame, and then we just give it the frames per second and the number of frames we want to go to, and we draw the lines, or draw all of the contexts into one big animation. The other thing that we do, which is a little bit different here, is we have a whole bunch of different layers, and these layers are set basically with, how do I put this? It is a vector of different frames where the frames are the animation. So we've kind of done a whole bunch of different animations on different layers. So we do, for example, the green dots here on one layer, the black background on another layer, and then the white lines on another layer. Okay, so what do I see that's wrong with this animation? Couple things. Okay, the lines are being drawn asymmetrically. I don't like that at all. Some lines are clearly off the screen. right? Like this one right here. And then the final one, the big one that really bugs me, is the fact that this guy never connects to anything. It's dead. It connects to nothing. So, when I clearly know, or I feel like I should know, that this is the spacebar which is used the most in the phrase that we're using. Again, the phrase we're using is Jack and Jill went up the hill to fetch a pail of water. Jack fell down, broke his crown. Jill came tumbling after. That's the one that we're using. And I know for a fact that the spacebar is used the most for this particular, what do I say here, phrase. And because of that, this one should be connected to the root node, but it's not. So we've got a couple of issues there. So what do we need to do? Well, draw internal. I feel like, oops, that was an accident. I feel like there's something wrong with a couple of these different guys. So let's go through and see what we can do here. So let's see. Every single position, we read in the root node, and then what we do is we push back the root node. So we should, at any given situation, have the root node available to us. So what we did is we read back regenerated nodes. What I want to do now is I want to go through and I want to just print out all those regenerated nodes without generating any sort of animation. So we have the regenerated nodes here, and actually I deleted this and I probably should have kept it in. So let me go into Huffman, visualization, .save, and let's scroll down to the main function here, main. And let's see, what do we have here? Regenerated nodes, dang it, I didn't keep it in this particular copy either. So let's go into Huffman, visualization. It's not hard to repeat, that's CPP. Okay, so here's what I'm gonna do. I'm gonna go down to main, and then I'm gonna go through, and instead of drawing external, which no longer exists, or setting any of this draw internal or draw layers, I'm gonna go down here, and I'm going to output these regenerated nodes, just to make sure that they are at the appropriate position. So let's do while regenerated nodes dot size. I believe I can do that. We'll see. Regenerated nodes. Regenerated nodes. Oh my gosh. Why can I not type today? Dot size is greater than 0. Okay. I don't know what I'm doing with this, but I'm just screwing up my typical notation. Okay, now we go down here and we say the following. Let's see. SCDC out. Regenerated nodes. Let's do it this way. Node star temp node. Just because this is a little bit easier to work with. And then say temp node. Temp node is going to be equal to regenerated nodes dot top. Then we say regenerated nodes pop. Pop. And that will delete the top guy. So now we're going to say temp node. We want to output a couple different guys. So let's output temp node pointing to X. Then what do we want to do? Good. We also want temp node pointing to Y. And then we want, one second, temp node pointing to weight. And that should be all we need. Let's write this, go over here, open up the make file real quick. And remove this convert thing, which is basically what gives us our graphics interchange format file in the end. Now let's make it. Let me see, temp node.x. Of course it doesn't because it's ori.x. And of course ori.y. Okay, now let's write this, go over here and make it. Give it a second to make and run, and let's see, we go up, and here's what we're looking at. So it looks like a weight of 127 is going to be at position 200, 0, which is exactly what we want. Fantastic. Okay, so let's see. The next highest one is going to be an internal node at 325, and the other one's going to be at 125. Now here are the nodes that we need to look out for. Some of these nodes are clearly over 400 in X, and that's this node in particular right here. it looks like it's only that one node. Oh, no, there's this one at 100125. Don't know how that one happened. Or this one at 1518. Or this one at 506. Heck, there's a lot of them that are way out there. These guys share the same X value and the same Y value. That's a little bit frustrating. Yeah, okay, there's a lot of them above 400, where our resolution is 400 by 300. So, I have no idea why that's happening. Let's go through and see if we can figure that one out. But, for now, let's just try to fix one thing at a time. The first thing I'm going to try to fix is why we're not drawing that root node, okay? So here we've clearly written out all the regenerated nodes, and it seems like at least initially, they're all starting where you'd expect. So let's see, we have 126. Yeah, sure, these are all fair enough. Sorry for the yawn, guys. Okay, so let's go up here, let's remove this, and let me comment in what I'm doing here. Here I'm gonna write destroying generated nodes and printing them out. Okay, now let's go down here and let's try this again. So let's go to draw internal, and I'm just gonna keep the animation up so you guys can all see our big mistake. And then we'll go from there. And again, guys, if you have any questions, comments, concerns, let me know and I'll totally get to them as soon as I can. For now, again, I'm going to get another sip of water because I'm incredibly thirsty. Okay. So, let's go down here to the draw internal command. Here it is there, and of course here it is here. So all we're doing is we're going through all of the regenerated nodes, where the regenerated nodes are a, wait, what are they? Queue, a priority queue, where the priority is set to the weight. So the one with the lowest weight is set up top, and the one with the highest weight is set at the bottom. And the highest weight is obviously going to be the root node. So if you looked at what we looked at before, let's go here. The highest weight is this one right here with a weight of, with a weight of 127, okay? Then we have, let's see, the next highest weight was 73 and 54. Obviously, if you add 54 and 173 together, you get 127. And so the idea is that this is a sum of all of the ones together. For some reason, oh, I know exactly why we aren't drawing the root node. That's because this should be a 0. Let's write this. Now let's go over here and let's redraw it. So I'm gonna go here. Write this, go into the make file, let's go down to convert, and let's get rid of this guy. Now let's do make one more time, and then when it's made we should have the root node being drawn, which solves one of our problems. The next problem I want to solve is figuring out why the two lines are being drawn at different times. So let's see what we got here. Let's do the Mirage Frames animation.gif. That's what we want. Okay, let's make sure the root node is being drawn. And it is. We are drawing the root node. Now, the root node is a little bit off the screen, but that can be solved pretty easily. So let's scroll down on all these images. And for the record, in case you guys are wondering, I'm using a very simple image viewer known as Mirage. And here is the, let me do a file. I think there's a thumbnail pane. Okay, so what I have here on the side is actually each of the individual thumbnails of all of the, here, let me go up here. So these are all of the different thumbnails for all of the trees we're working with, right? So I figured I'd let you know that every time you see me kind of scrolling and stopping at a particular image, all I'm doing is going through these thumbnails. At the very start of this directory, we have the animation, which is this one right here. So I'm letting you guys know that's there in case anyone was wondering. Okay, so now we are drawing the initial root node, but now we have that other problem that I was mentioning before, and that is that these lines are being drawn asymmetrically. So let's wait for a line to be drawn here. Okay, and you note that this one's already done, and this one's still being drawn in. So this means that the initial time frame that we're giving these guys to work with is, for some reason, not correct. So why is it not correct? I'm not sure, but it looks like it's 1 frame off. So let's do this. And I know this is kind of a cheapo way to do it. Let me just add a 1 here. Right here. Go over here and let's make it one more time. Yeah. Okay. Now let's take a look. Once it's done. And then we'll worry about the X and Y positions after that. So let's do Mirage Frames animation.gif. And let's see. Oh, that just made it worse, I think. 1 second. 2. Wait. Really? Let me see. Maybe because we have to add in the FPS. Let me see. Frames per second. If there are 10 frames per second, which there are in this particular, I guess, visualization. It's not really a simulation. Let's see. So we have animation. Animation current frame minus time divided by num lines. Oh, okay. I know what I need to do. The following. Plus 1. Let's go over here. And let's draw it one more time. Make. And then hopefully all these minor things will be fixed. And we can go from there. So I think the problem is in the integer division when we do time divided by num lines. So let's see what happens. Let's do Mirage Frames animation.gif over here. And let me see. I'm not noticing it, but it might still be there. Let me see. Down 1. Yeah, okay, so they look like they're being drawn at the same time. Yes, good. Exactly the same time. And that's what I want to see. So now the question is, why is this happening? And that I'm not really sure. So let's change this to maybe a double. And then let's remove the plus 1 at the end. And let me see if this fixes anything. I've got a feeling it might not. But let's just see anyway. Okay, give it a second to run. And now we're going to look at the animation. Another beautiful day on this lovely island of Okinawa. Let's see, the sun is shining. I imagine the birds are doing their bird thing. Okay, let's scroll down. No, okay, so this is still broken. I'm just going to leave it as it was before and just not worry about it. I'm going to add a plus 1 at the end here. And we'll worry about this if the issue comes up again. The issue is that we're going to be like 1 or 2 frames off. And in the grand scheme of things, when we have maybe 30 or 60 FPS and we're doing the same simulation again, is it really worth it? Probably not. Okay, so we have the animate lines. And just for the record, let me very quickly go into what we had before versus what we have now to show you why we did what we just did. So let me go into Huffman, or VI Huffman, visualization, .save, .cpp. Now let's go down to draw internal. Okay, so draw internal is right here and right there. Okay, so the draw internal function here is really, really large. It's here. Let me scroll down. Here's the start of the draw internal function, and 1 second. I'm not there yet. There's the end. So it is. Let me see. Set number. It starts on line 390, and it ends on line 469. So this is a, let's see, 390, 70, 80 line long function that we've now abbreviated down to like, what, maybe 20 lines. So we've cut a lot of lines here. And now I know what you're thinking. There are a whole bunch of, 1 second. There are a whole bunch of lines in that draw internal function that we had before that were, commented out. But even removing those lines, the draw internal function now that we have here is much easier to follow. So let me go ahead and comment in what we're actually doing. So we're going through, let me see. And let's do this. Going through, goring, going through all regenerated nodes and drawing the lines to the internal nodes. Now, what else do I need to say? ignoring external nodes, which have been drawn in, one second, the draw tree function. Gosh, come on, pretend I can write function. There we are. And here we are there. Okay, good. So now the internal nodes seem to be drawing. Okay, so now we have to figure out why the X position is going absolutely crazy in the draw tree function. So where are we in draw tree? Grow circle. That's fine. Let's see. Create frame. Also fine. We're down. Gosh, sorry about the yawns, guys. We're down here somewhere. Draw tree, right here. Okay, so what are we doing? We start with an X position at 0.5, which is right in the center. Then what we do is we go through and we give these guys a new X and a new Y position. Okay. Hey dude, what's up? So then we go through, we say draw tree, animation, let's see, X plus 0.5 times X, root right level. So here's where I think things get a little bit screwy. Let's go ahead and draw this out. So here, let's go here, let's do page, new page before. Okay, so not much, man. Thanks for asking. So we start at a position of 0.5. Okay, then what we say is we go here, and this is 0.25, or here, which is 0.75. Then what we do, what am I animating? I'm animating Huffman trees. I think, let me go to my stream real quick, unless I screwed this up. Yes, so the top of my stream says Huffman Forests. That's exactly what we're doing. We're animating Huffman trees to create Huffman Forest, essentially. We can get into what that is if you have a question on it. Okay, so what we say is we move it to the right or the left, depending on what the X is that we've read in. However, what we should probably do is something a little bit different. We should probably say that we move it to the right or left, depending on the level at which we are at. And let's mess it up a little bit. So a Huffman tree, just because some people are new and they haven't seen this before, a Huffman tree is a way that we go from a string, let's say A, B, C, D, E, into an encoded string of, in this case, 1, 1, 1, 0, 1, 1, 0, 0, 0, 1, 0, 0, right? And the idea is pretty straightforward. We draw the tree out like so, by saying, let's say A has a frequency of showing up of 0.7, B has a frequency of showing up of 0.15, and D has a frequency of showing up of 0.15. We add the two lows together to get 0.3, and then we add the two lows together again to get 1, and we say we have 1, 0, 1, 0 along the branch. So A will be 1, B will be 0, 1, and D will be 0, 0, reading from this direction, so 0, 1, 0, 0. If we have a string of A, B, D, then this will be 1, 1, 1, 1, 0, 1, 0, 0, which is in a sense optimal because we have so many more A's than we have B's or D's. In this case, we have shortened the number of bits in the end. So the Huffman tree is a way to do some sort of crazy encoding scheme that allows us to use a minimal number of bits for the encoding. So it's compressing that data. And at the same time, we are drawing an intuitive picture for how to do the compression. And so it's kind of neat. I think it's really cool. Okay, so that's kind of what we're visualizing. Now, let's go back to how we're drawing it. So what we're doing is we're saying we have an initial position of 0.5, which is absolutely great. That's what we want. Now, after that initial position of 0.5, we then say, okay, well, we have a whole bunch of different levels. And we're doing something kind of weird here that I think is kind of breaking it. The problem is we then say, okay, we're going to be adding half of the value that we're currently at to the left or to the right. So what we're doing is here, we're going to be adding 12.5 here. Sorry, 0.125. And then here it's going to be 0.375. However, for this 0.75 here, if we subtract out half, we're going to be at 0.3, 0.375. 0.75, I think. And then here, if we add half, we're going to be at 1.0. Sorry for the drawing, guys. 1.0. Let me see. Something. 1.0. I think 1.11. Something. I'm really bad at adding right now. 1.11. And that's the issue. So let's go ahead and fix this up. This clearly will have the points outside of the range. This is something that I kind of saw yesterday, but I don't know. We'll go from here. So what we need to do, it's okay, Gustron, don't worry about it. What we need to do is make it so that X is dependent on the level that we're at. And this will kind of help out a good bit. So the new X position is not going to be, rather, we're going to keep it as X like it was before. But then what we do is down here, when we draw the tree going to the right or the left, we give it a new X position. And the new X position is going to be dependent on the level that we're at. So let's go. We're going to say, what do we need to say? We have the initial resolution of the grid in a way. So if we're at 0.5, we've divided it by half, right? And we've already done this calculation before. But if we're at 0.5, we've divided it by half. So that means we then have to divide it by 4. If you're a CD Ninja. I guess I do. Thanks for coming in. You can actually just calculate X value at every level. Yeah, that's kind of what I'm going to be doing here. So what is the X value going to be done? Or going to be... What am I going to be doing with this X value? Okay, so if we're on level 1, the X value is going to be 0.5. Or level 0. The X value is going to be 0.5. Then if we're going to be at level 2, the X value is going to be, let me see, 0.25. Gothic Death Eater, ohayo gozaimasu. Yes, and I guess, konbanwa to you. I don't know what time it is, but it is probably in the evening for you. Okay. So what do? Here's how I do it. Pass total X, parent X. Here, let me see. We don't need... We're probably pretty good here. So we already have, let me see. Here's what we need to do. We already have X here. We already have the level, right? I speak anime? No, I live in Japan, so I have a little bit of help here. So yeah, actually, Gustron, I think that's exactly what we did previously. So let me go here to the draw internal command, which was here, and we had to find X position here, and we did power of 2 a double of I plus 2.0. So we did, I think, basically the same thing. Oh gosh, let me see. Oh, it's 21st hour, so that would be, gosh, I'm so bad at Japanese. I need to learn it more. In fact, I should probably have spent my time yesterday doing that than what I actually did, which was a waste of time. Let me turn on the air conditioning. It's getting kind of hot in here. Okay, so let's see. We want to do something like what Gustron's saying. So here's what I'm going to do. What do we need to do? Title League, what's up? Let's go down here. And what do I want to do? That would be the time that everyone uses. Yeah, I know. It's depth from root. Depth first. What? Wait, what? Kind of. Yes, in a way, we are doing a depth first search. In a way. Okay. So what we need to do is find the actual resolution of the grid, which isn't so bad, right? Because we already have X and we have the level. So if we have X and we have the level, let's just recreate the actual grid resolution every time. So let's go down here and let's say resolution X. Here, let's do double. Resolution X is going to be equal to the following. Okay, sure. So what are we going to do? Let's go through resolution X. And this is going to be equal to the X position that we have. Oh, fair enough. This isn't going to make any sense, is it? Okay. Yeah, so we might need to read in something every time, which is fair enough. But we're already reading in the frame animation, so we already have the resolution X. I just realized that, and I'm an idiot. Okay, so we already have the resolution X. Let's see, what did you say before? Yeah. Yeah, so the total X we already have. Because we totally already have it. Okay, so now what we need to do is the next thing, which is the following. So the next thing, which is the following. Wow, I'm being super redundant. Let's do... wouldn't that be naming used for total resolution? Yeah, the thing is, in our animation box here, let me go up to the top. We already have resolution X defined in our animation frame. So I don't have to worry so much about that. Now let's go down to, where were we? Draw internal again. And let's do it. So before we did, plus equals or minus equals animation resolution X divided by power of double 2 of I plus 2.0. So we're going to do the very similar thing. Wait, what's wrong? Wait, wouldn't that be naming used for total resolution? I do very similar naming conventions. I think the naming conventions I figured were all the same. You have, I usually do lowercase and underscore. What would you guys want resolution X to be? Like, what would it be called? I don't know. It seems to me like fairly standard. The only thing that I do that annoys Gustorn, I guess, is I capitalize people's names. So like Monte Carlo would be capital MC. But I don't know. Okay. So let's see. Where are we? We're on draw internal. And what do we need to do? Resolution X? Wait, what? No, it's not. Resolution X is the total resolution of the entire frame, right? It's not the last level of the tree. It is a resolution. In this case, it is totally a resolution. It's defined up here in our struct for the frame. Now, I'll admit frame could have been named better, but that's okay. It is actually, so in this case, if we have a 300 by 400 image, it will always be 400 in this case. So this is the actual resolution of the image. It definitely is. I have no doubt about that one. Okay, so let's go down to draw internal. And let's go from there. Here. Okay. So where was I? Oh, it's draw external. That's why I was getting so confused. Let me go to draw external. No, it's... What am I looking for? Draw tree? There's draw tree. Yes. No. Yes. That's what I'm looking for. Good. Okay. So here's what we're going to do. It's going to be the maximum width of the last level of the tree. No, it's not though. This is the actual resolution X. We never modify the resolution X. So here's what we're going to do. No, resolution X is always going to be the resolution of the screen. No matter what. It's always going to be the resolution of the screen. This algorithm frame animation is not modified. Resolution X is not modified. It is exactly the resolution of the screen every single level. That's why I read it in. So we're going to do the following. We're going to say, in fact, if we, yeah, so here we actually use it, right? Anyway, it's fine. So we'll say the following. We're going to say, let's say dx. So let me go up here and say double dx. Go down here. And we're going to say dx is going to be equal to animation. Actually, we could probably do it up here. Dx is going to be equal to animation.resolution x divided by just wondering, I know this is a bit off, but do you know what concatenate means? My Java teacher says a lot. I'm not sure about it. Well, dude guy, basically... No, I'm sorry. I'm not angry. I apologize if it seemed like I was angry. Sorry, Gothic Death Eater. Totally not angry. Okay, So let me see, dude guy. Concatenate basically means usually used in the frame of strings. You have two strings, you push them together. Yeah, exactly like what Gustron says. You put things together into a single, I guess, structure of some sort. So you can concatenate strings. I could say, sorry about that, I hit the desk. I could say that I am concatenating, I suppose, a whole bunch of frames here in a way, putting it into a central file. Again, it's just pushing things together. Animation resolution X divided by power of 2. Then we do double of level. Then I added 2, but let me add 1 and see what happens. And good. So let's go ahead and write this. And now we're going to go down here and say plus dx, dx, and then minus dx. Let's go over here, right and quit. And now let's do make one more time. Now this is going to run into the same situation we had before, which was that the following. 1 second. Let's go ahead and draw it. Some of the X dots are going to be over some of the... oh, actually, wait a minute. This is a little bit different than I expected it to be. Let me see, what did I do wrong this time? So let me try changing this to 2.0. And let's do make. Give it a second. I think this should fix the problem. I'm trying to remember why it had to be 2.0. And I think that's because the level is off by 1. So we add 1 for the level being off by 1. And then we add 1 to get onto the appropriate frame. Let's see. Yeah, so these look like they're all at least on the screen. Yes, so that's kind of what I wanted to draw. Were you looking for symmetry? No, I was not looking for symmetry in this case. Okay, but this is, I think, exactly what we wanted to draw, which is, okay, that's fair enough. Okay, so now let's go ahead and increase the X resolution a little bit. Let me go up to the top. And let's see. Yeah, basically you're right. Okay, so now what do we need to do? I'm going to go up and I'm going to change the X resolution to see if that fixes something. And let's see. I don't think 1.0 is correct. Because no matter what the X resolution is, those points are going to be off the screen. I think 2.0 is correct. But we can change this. So let's do this to, let's change the X resolution to be, I don't know, 1000 or something like that. And then let's change it back to 1.0. I think 2.0 is correct in this case. Let's go here to 1.0. And you'll see that this is still off the screen because resolution X doesn't change. So no matter what, this is going to be scaled incorrectly. But, I mean, we can try it real quick. Okay, this time we're going to make the animation, but I'm not actually going to look at the animation. I'm going to scroll down through all the points. Reason being that this image is a little bit bigger, so the animation is going to look a little bit messier. Based on the scheme that we're using. So let's do, yeah, resolution is if we're measuring in pixels, exactly. So let's do this, and I'm just going to scroll down. Okay. Yeah, so these points are still off the screen, no matter what we do. The root should be resolution 2. Root is at level 0. Resolution 2 raised to 0. Why wouldn't you? Why wouldn't I what? 2 raised to the 0 plus 1 is resolution divided by 2. That is correct. However, we're starting at 0.5, right? So if we're starting at 0.5, we're already at 2 to the first. The next thing we have to do is divide it by 0, is add 0.25, which is 2 raised to the 2, right? So if we're at level 0, and then we have to add 1 to that to get 1, then we should be, I think it's because I'm starting at level 0 instead of level 1. If I was starting at level 1, I think you'd be totally right. So let's go here, and in draw tree, let's change this to a 1. And I think this should solve the problem too. So let's do make. 1 second. No, I'm not special casing root. We just start at, 0. or we start at 0.5. That's the initial position of root. No, you're perfectly fine. I'm totally measuring in pixels. Sorry, Gothic Death Theater. So let's do Mirage animation.gif. And I think, wait, let me see. That should too fix the problem. Yeah, so this also fixed the problem. So it depends on what we want to start with. Because I started at 0, it was a little bit different. Okay, so now we have another issue. That is, no matter what X resolution I choose, I'm going to run into this situation here. And this is a situation I was trying to fix yesterday, where unfortunately some of the points are being overwritten. We can stretch Y a little. Let's go up here, 1. But we're still going to run into the same issue. So let me go down here. What am I doing? Let me go down to where we initialize everything, which should be in main. And let's put this at, I don't know, what's a standard resolution? 1000, what is my resolution? It is outputs. I've done this before, by the way. I always forget. 1920 by 1080. Let's do 1024 by 768. Close this one. So 1024 by 768. Write this, go over here to make, and give it a second. Thought about writing a function to check to see if a point already exists or not. I have thought about that. But it's a matter of, I don't know, I haven't figured out exactly how I need to do it. I think you're multiplying y by something and draw a tree. I'll take a look at it. So let's go down to draw a tree. And let's see. For the draw tree command, we're going through, let me see, here. And yeah, I'm multiplying it by 25. It's just an arbitrary number, which is fine. Ideally, it will be set differently. So it should be set by the number of levels that we have. And let me think. How many levels are we going to have? Mirage animation frame.gif. Let me see. So looks like these are off the screen again. Oh no, the animation is off the screen. Good. Okay. So how are we going to set this? How many levels do we have? We have 1, 2, 3, 4, 5, 6, 7. So let's do this. Times animation dot resolution y divided by, let's say, 8 for now. So let's go here and let's try it one more time. Make. Okay, give it a second. And we'll see what happens. It takes a little bit longer to run because we have super high resolution in this case, but that's okay. It's a good test case to work with. Okay. Good. 1 second. We're waiting for it to make the next animation. And I still feel like I'm doing something a little bit wrong with this, but we'll see what's up after this one's being drawn. You actually have the height of the tree is the length of the longest bit string containing the Huffman code. Oh yeah, fair enough. Let me see. Node Q animation. Let's see. So let's go into Mirage animation.gif. Let's go down a couple. 1 second. Okay, so it looks like I have everything almost right here, but not quite. So let's see, what's that? I'm just gonna do this manually for now, and then we can do it non-manually later. I think the answer is actually 7.0. So let's go here, 7.0. Let's write this, and let's make it one more time. Okay, so now the question is, what are we reading in? We're reading X, root, int level, node Q, regenerated nodes. We are not reading in the Huffman tree. We could read in the Huffman tree, which would have the bit strings that we could work with. Or we could just read in an integer value that is always the same. And that's another way to do it. Let me think. So the longest string is 7 in this case. So I guess we'll add that in just a second. We have draw tree. Where's draw tree being called? Yeah, I think we can just pass the integer without too much trouble. 1 second. Now let's go into Mirage. Frames. Image 0, 0. Just going to the very first image. Okay, now let's scroll down. It looks like these are correctish, almost. Not quite. I mean, they are correct. It's just a matter of the angles are not quite right because of how I'm doing this. So I think what Gusthorn wants is a tree that we have. What kind of coding is this? As in what language? The language is C++, and we're using a graphics library known as Cairo. Let's change it back to 8. Let's go here and make it one more time. In terms of the environment that we're just using VI, which is just a basic text editor, and then we're compiling it. It's C++. Yep. Definitely C++. Okay. Sorry, I guess I answered twice. Okay. So give it a second to convert this again. Actually, we don't need to convert it every time because we're not even looking at the graphics interchange format file. There's a few things that I don't like about this visualization. Let me think. Now, one thing is that because of how we're currently visualizing Y and everything, no matter what we do, I think we're going to have an angle kind of arching in here. And let me think. We might be able to fix that, but I'm trying to think of how we would fix that. Animation resolution X. Okay, I think I have an idea of how we might fix it. So let's do the following, and let's scroll down. Okay. So here we're using it more Y space, which is great. Let me try dropping the Y space down one more little bit. So let's change this to 8.1. No, let's change it to 8.25. And now let's do make. And the reason I want to do this is just to kind of shrink it so all the dots are actually on the screen, which they are not currently. I'm not sure if this is actually going to fix the problem or not, but hey, we might as well try. If you implement one of the more complex tree visualization algorithms, it organizes subtrees better. Yeah, we could do that, but I'm trying to think of what we actually need to do for that right now. And then we'll worry about that when we get to it. Okay. So, what do we need to do? Give it a second to convert the animation that, again, we're not using, so I should probably stop that. Actually, I probably can, can't I? Okay, let me go into the make file, and let's remove that function there. Right and quit. Now let's do the last Mirage. Let me pull this over a little bit. Scroll down. Okay, so now all the dots are being visualized on the screen, which is great. That's what we want to see. Okay, let's go ahead and read in the level. Now, a couple of things to note here. One thing is that, let me go up a little bit. Yeah, the thing is, I don't know. Okay. So, let's see. What do we need to do? Okay. So one thing to note is that no matter what, we're going to have this arching happening here. I'm going to try a couple of different things just to see what they look like, and then we'll kind of go from there. So, what do we need to do? Let's change how we're visualizing Y for now. Because it's actually the same image that we had a few days ago, but it's a little bit cleaner drawn, so that's okay. Then we'll go from here. So let's do root pointing to Ori Y. And let me see. I just want to try visualizing it by weight again. It's going to be equal to root dot weight divided by 127.0. I just know that's the maximum weight, so I'm just reading that in. And let's see what we got. It should be root pointing to weight. Root Ori Y. So this means the maximum weight will be at the very top. Good. Oh wait, no it doesn't. We need this. Let me think. 1 over this. So let's do 127. divided by root weight. Root pointing to weight. Then we need to multiply this factor by, let's see, animation, 1 second, times animation.resolution y. Let's go over here, write this, and let's do make. Give it a second to do its thing. We shouldn't be converting it into an image anymore, so it should be a little bit faster. And then let's see what we got. So let's do Mirage animation. And looks like we have nothing. Fantastic. What did I do? Root or EY. 127. Root weight. Animation resolution Y. Okay, so if root weight is 127, that means we're at the top. It should be 1 times animation. Oh. Oh. I see what I did. My bad. Let me think. Root weight. If this is 0, let's do divided by 127.0. And then we're going to do 1 minus this factor. Then we're going to multiply that. Let's try this. Sorry about that, guys. Good. Okay, give it a second to finish making, and now let's go Mirage animation. Let's see what we got. Okay, so here are all the dots, and there we go. Okay, that looks pretty good to me. Good. I mean, tree's a little bit wonky, but that's okay. The other thing is it's obvious that all of the leaves are kind of stuck at the bottom. Now let's see. Let's try another string. Instead of what we were doing before with Jack and Jill, let's go up to the top and let's just try some simple strings for now. Just to kind of check this out. So what do we want? Let's do this. I'll put these guys. And then let's do the following. Oh, sorry about that. We're going to do Huffman tree. Final tree. It's going to be equal to 2 pass Huffman. And then we're going to read in a string. And the string is going to be yo, yo, yo. 3 characters. Each weighted 3 times. Oh, no. 2 weighted 3 times. 1 weighted twice. Then we're going to do decode. Final tree. And now let's go ahead and make this one. This should be super easy compared to what we had before. The weight in the end is going to be, I don't know. Let's go down here. Scroll to where we did 127. Let's see, 127. Let's change this to 9 or something. Let's go down here and let's do make. It's going to be way faster to do, I think. Wait, the resolution's still super high, but that's okay. Now let's take a look at this tree. Should be relatively simple. And let's do Mirage animation. There we go. We've got a space. Down here is the least used character. Y is the most used character, and O is the most used character. They add together here, and then they add together there. Good. Okay. So simple trees work just fine. Complex trees seem to work okay. Now, again, we run into a situation where, how do I put this? Again, the tree doesn't quite look the same as normal trees, and I will totally give you guys that. This is something that, again, Gusford mentioned before. There are some way more complicated visualization schemes. At this point, we're at a position where we can visualize things okay. We just kind of have to work from there. So the one thing that we have to figure out is how to visualize the x-axis a little bit better. Because again, if we go back to our other scheme before, let's go to main, and let's go down here. Remove this line, and these 2 lines. Write this, go again, and make it one more time. you'll see that there are some positions that have all the x positions clumped together. So we have to figure out how to fix that. I'm not really obvious. It's not really obvious to me. And again, this is Gusper mentioned before. People have papers written on this, so it might be that I just have to reference one of those and work on that tomorrow. Now the thing is, I did reference one of those, but apparently I referenced it incorrectly. So let's scroll down here. So here's the exposition thing that I'm talking about. If we zoom in, let's see, how do we zoom in? Control scroll. Then can we move down? Yeah, we can. All of these are right on top of each other. So we have to figure out a better way to visualize those subtrees. But the X and Y positions are, you know, pretty easy to manipulate. And I like that. That's pretty good. So let's move over here because we have another situation here. And we also have this one square that is being drawn incorrectly. But I suspect that's the new line. So let's go ahead and remove the new line at the end here. And just pretend that no one would ever put an enter into a Huffman tree. Let's write this. Let's make it one more time. Okay, give it a second to do its thing, and then we'll go from there. Okay, so let's open up the image. Let's scroll down a little bit. This tree looks... Oh, I know why the tree looks dramatically different. Let's go down to by 1920 resolution. Yeah, we can do that. Let me go to 9.0. Here, let's change this to 127. Let's go up to the top, and what is it? 1920 by 1080, I believe. So let's go 1024. 1920 by 1080. Right, this. Then we're going to make it one more time. Give it a second to run, and then we'll see what happens. It's going to take a little bit longer to do its thing, but that's okay. Give it a second. Sometimes it takes a while to run. Okay, almost there. There we go. Okay, so now let's go ahead and open it up. Mirage image. And let's scroll down. Okay, so we put them all together. That looks okay. Now let's try imaging them instead of by weight, but by level. Let me go down. Let me see. What do we have here? In it. Grow circle. Animate line. Internal. Draw tree. It looks similar. Let me go here. And do this. Write this. Go here to make. And let's give it a second. It'll look the same, but it is dependent on the size of the circles, right? So we could lower the size of the circles and that would be fine. Again, we just have to find a better way to visualize the subtrees. And you're totally right. There's probably people who have written plenty of papers on this, so they know way more than I do about it. And I guess we'll just see what we need to do from there. So Mirage, image, let's scroll down. Okay. This tree looks phenomenally easier to read than the other one that we had. I'm not sure why. It shouldn't look that much better. So let's go here. Let's change the resolution again. Back to what it was before at the very start, which is 400 by 300. And the reason I want to do this is so that I can see all of the issues. So let's go to 400 by 300. Write this, go over here to make it one more time. It'll take significantly less time to make. There you go. Mirage image. Okay, so now we see all the issues coming back. Okay, there we go. Good. Yeah, I know. But the reason it looks better is simply because we have given the dots a static size. And so because we gave them all a static size, they are smaller when we have a higher resolution. So it looks a little bit better. Okay. So let me think about this. We got plenty of things that we could do. But, you know, it looks to me like we have a dot at pretty much every X location, right? We don't want to change the Y locations because that gives information that's not correct about this simulation, right? So if we have to change the X position, we have to find places to further space out these positions, right? So let me think. What we could do is, we could give the root nodes, or the nodes at the end, a little bit extra space. So let's do this. And just as a kind of quick test, we can just do that. So let's go down to grow circle, draw internal. Where do we want? We want draw tree. Okay, so if root right, if root left, we then give it a new X position or Y position. Then what we do is, if there is no left or right, yeah, I'm kind of doing at every level. Why would I want it at every level? Let me see. Oh, I see what you're saying. Sure, we could do that. And the static offset could be the, let me think. Yeah, sure. That's actually not a bad idea. So let me do this. Let's say resolution X, and then we're going to add in 10. With this, go to make. And now let's see what happens. Mirage image, scroll down. Oh, I think I added them in the wrong direction. Also, I'm not really sure what I did there. Oh, it's doubling up. Why is it doubling up? Okay, wait, let me do it this way. Instead of adding the 10 here, let's go down here. Let's see, plus dx. So this is going to be to the right, and we want to add this one a little bit. We want it to go over a little bit. So let's do plus 10 there. Oops, my bad. And I guess minus 10 here. But that should be the same thing as adding 10 up to the dx. Let me think. So if we're going to the left, we give it a little buffer, and that's fine. If we're going to the right, we give it a little buffer. Wait, let me look at this again. Go up here, add a plus 10. 10. Go over here, make it one more time. And then we'll take a look at those images. So, Mirage image 00.png. First one's a blank image. We generate all the dots. Maybe 10's a little bit too small. Let's try 20. Make it one more time. Oh, sorry. Make. Okay. Now let's see what happens. So we're going to do Mirage image. Move over here, scroll down. Some of them are off the screen, but that's relatively easy to fix. Okay, so that F. Oh no, that's good. Actually, all of these nodes seem off of each other. These all seem okay, I think. 1, 2, 3, 4, 5, 6, 7, 8, 9. Let me see. Let's check this L. Oh, L and O are right on top of each other. Okay, let me see. Which shouldn't happen. Yeah, unless we have a situation where the following happens. So, page, new page before. There is a case based on the current visualization scheme where we have one here. Let's go here. And here. One guy here. And then we come together. And let me think. No, that one right there was not weight-based. I flip back and forth. So the one that you just saw was not weight-based. This is, that's not. That's just your standard level 1 that we were talking about before. Again, if we do weight-based, these are way more linear than if we don't do weight-based. So then it shouldn't happen. What shouldn't happen? Oh, the fact that they're overlapping? I mean, kind of. So let me go here. Let me think. Let's see. They aren't directly overlapping, I don't think. Okay, so they're only overlapping with the offset, I think. Cancel. Let's remove the offset. Right, and let's go over here to make. And then let's go down. Image. Okay, so if we draw this, that's 1.2.3.4.5.6, 7, 8. They're not directly overlapping each other, but they get incredibly close to each other. Which I guess kind of makes sense, because if you're at level... let me think. If you're at level 7, which is the maximum level here, 2 raised to the 7th is... wait, what is 2 raised to the 7th? So they're just super close. Whatever 2 raised to the 7th is. And then we multiply that by the resolution x. It's super close. Which is why the offset's a good idea. But I've got a feeling that maybe we should only do the offset with the final nodes. And then if we give these guys an offset, you know, it ends up being that this level moves over a little bit, this level moves over a little bit, this one over a little bit, that one over a little bit, so it goes off the screen. So then we have to think about how to, I guess it's not that big of a deal. Here, let's see what happens if we do this. Thanks, Untello. I'm really bad with powers of 2. Okay, so let's add 10 here. And then what do we want to do? We want to do dx is equal to this. Animation resolution x. We add 10 there, but we want to divide it by plus 1.0 power of 2. We want to divide it by, I guess, let's try this, plus 10 times level, plus 10. Let's do Mirage. Oh, wrong one. Sorry. Let's do make. 1 second. Make. Now let's go from there. Okay, give it a second to make its stuff. Mirage image. Scroll down. Okay. They aren't quite overlapping as much in this one. That doesn't look so bad. So let's give it a little bit of a different offset. Let's change this to 20. And 20. Let's go to make. Then we'll take a look at this one. Okay, these guys... Oh, okay. Now we're running into the opposite situation. Ugh. Yeah, it's all mixed up. I'm trying to figure out what's exactly happening here. I think the other one, you could clearly tell the nodes apart. So let me go here. Let's remove these. And remove this one here. And let's go here to make. And then, so this one, just the original one, you can clearly tell the nodes apart, right? So here, even though they're overlapping, you know where all the nodes are because they're being connected by internal nodes. So here, you know exactly what's happening, right? So let's try something else then. See, what I want to do is, let's see, X. And if we're doing this down here, let me see. Grow circle, radius of 10, animation, time of 0.25. Oh, sorry for the yawn, guys. Okay. Now, what's the X and Y location of this guy? Root origin. Okay, let's go here and let's add in another origin. So we're going to say up here. Yeah, this is fine. Position, temp, origin. Let me see. Just increase the X resolution. It will help a bit. And I'm late again. That's okay, Zivo. Don't worry about it. You can, I mean, again, hanging out with friends is, in my opinion, more important than a programming stream on the internet. I mean, I realize we're also friends, but I'm here every day, you know? So if you want to hang out with friends, of course that's, you know, totally worth doing. Okay. No, the offset wasn't a bad idea. I'm just trying to think of what we want to do from here. So how about, let me think. Do we have access to all of the parent nodes? Let me think. So the issue is that these final nodes. Man, I'm tired. I'm sorry, I've been yawning like crazy. These final nodes need a little bit of a better position. So let me think. How are we going to fix this? My suggestion before was simply to give them a little bit of an offset depending on if they're an external node. So if the last one is an external node, then we give them an offset dependent on the radius, right? So that's something we can totally do. I'm just trying to think of how we do that. So the idea here is that if we go to the image here, we scroll down. Let's just have the whole thing. And let's scroll in, why not? Move down a little bit. So these guys are just super close together. So what we could do, because this is on a completely different level than everything else, is we could give these guys a bit of an offset dealing with the radius of the circles that we're drawing. Hey, Edge226, I'm doing perfectly well. How are you? Okay, but then we run into other situations visualization, which is a pain in the butt. If you scale the offset with 1 level plus 2, yeah, we can try that. DD, oh, that was an E, I wanted a D. Let's try level plus 2. But I think this is going to be opposite of what we want. Alright, Patrick OMG, have a fantastic evening, night, sleep well, etc. Okay, so let's do Mirage Image 00 PNG. Yeah, that just makes them all closer. Let's do to raise to level. Make. Okay. And then we're going to do Mirage Image 00.png. This one helps a little bit, but there are some that are off the screen. Screen. Dang. Okay, so let's go here. What I'm going to do now is I'm going to leave this at level +1. Right, this. I wouldn't grid structure be easier, like holding the letters in a 2D array with 1-2 tiles between them, and then drawing from there. After that, doing the branches. I may think bad, but I'm just trying. Let me think. So grid structure. So what you're saying is we hold all the letters, have a constant offset. We could do that. Wouldn't a grid structure be easier, like holding the letters in a 2D array with 1 or 2 tiles between them? Yeah, actually you and Gustrin have a very similar idea here. So let me think. So what we'll do is dx, let's just set it into something silly. So let's do this. How many letters do we have in the end? 27 or something like that. So let me just do a static thing here. Let me do... What am I doing? So we need to figure out how far it branches out. So let's go down here. Let's do double dx. Is going to be equal to animation dot resolution x divided by, let's just say 30. And let's see, yeah, maybe this will work. So let's go here and let's do make. Give it a second to do its thing, and now do Mirage Image. Oh, these are clearly overlying on top of each other, but we have a straight yeah, Huffman tree. Wait, let me try this again. Let's try 20. This is the issue we ran into the other time. I remember now. So we do Mirage Frames Image PNG. So let me do, oh, sorry about that. Make. These are always going to be overlaying on top of each other. I just remembered, because we totally tried this before. Yeah, we totally tried this one before. That's fine. You're okay, Zivo. Don't worry about it. I mean, if you see the number of times, the way I see it is this. Whenever you try to do something, yeah, exactly. Gusrin said the same thing. Like, here's the thing. When you're learning something, when anyone's learning anything, like I'm learning on here, other people, I hope, learn on here too. you always say things that are incorrect. You continually say incorrect things over and over and over and over and over again. But eventually, you keep working on it, and your incorrect assumptions eventually kind of average out, you know? And so your suggestion is not bad. It's really good. It's just, again, as Gustron said, we need to kind of think about it some more to get it to work. What you have right now is broken. Okay, so let me think. The issue here is the following. Well, okay, so Gustron, it looks good except for this. It's also kind of hard to read. So this is... Here, let's scroll down. This to me is incredibly hard to read because... I mean, I don't know. I think it's ambiguous. But anyway, it's fine. So here's the issue. All these dots are overlaying each other. Let's scroll down. So we have a whole bunch of dots that are just right on top of each other. Right? So that's not right. So let's go from there. What I'm going to do is the following. I'm going to comment this guy back out, comment this guy back in. We're going to go here, we're going to make that one. Because this one is actually correct, at least in the visualization. Again, I kind of like doing it with the weights, but we have to do the weights later anyway. Okay, so I'm going to go ahead and commit this version to GitHub, what we have right now, so that you guys can mess with it on your own if you're interested. So let's go ahead and write and quit. Then we're going to do git commit Huffman visualization .cpp. And then we're going to add in, we could do the encoding on paper. I thought that, wait, I might be misunderstanding what you're saying because I think that is how we did the visualization or the encoding on paper. Oh, I see what you're saying. Yeah, let's try that one real quick. Why not? So let's go here and let's see. What do we need to do? Let's say adding in simple visualization scheme of standard Huffman tree. Right quit, git push, origin master. Yep, I'm sorry about that. Truth be told, if I run a git status, it's really messy. But the problem is, all of this stuff in here, all this modified stuff, that all should be deleted. And stuff like that. So it's just, I've been working on this for like a year now, and there's just a whole bunch of stuff that I should really probably put into my git ignore file, because it's stuff that I don't want to delete, but it's stuff that I don't want to, but I definitely don't want to commit. So it's just a whole bunch of random stuff, because we do a whole bunch of random visualizations on this channel. It ends up, that happens a lot. So let me scroll down. Here's my info. Go to github.com down here. Click that. And then you'll have access to the code under Huffman, Huffman visualization.cpp. So here's the file that we've been working on. Okay. So, making think for a vacation. Monte Carlo. Wait, is Monte Carlo a location? Holy cow. It was, I already clicked on this before. Okay, well, that's something I learned. Give each node a size, 0 if it's a leaf, higher based on its children, then offset its parents by a plus b over 2, where a is the size of the left child, b is the size of the right child. Yes, so, this is something that we have considered. Frank3434, did you change your name again? Seriously, man, you changed your name more than, like, other people. Let me see. Zivo25, trying to hold all used positions and checking if there is already drawn there for avoiding a written. Yes, we could also do that. Let me think. But then we run into an issue where, let me think. Your friend Gustorn is here. Um, that's fine, Frank 34. Okay, so what do we need to know? Let's go and let's do Mirage image. So, what do we need to do? We need to figure out how to fix this. So we can do a number of things. I'm going to try something. Now, what Gustrun suggested was actually, something that we could do. Let's go down here. I didn't think that was passive aggressive, but that's fine. Okay. So what we do all the time when we do the visualization on paper is the following. Here, let's do this. I'm going to just put it here. If I might make a suggestion, you can dynamically calculate your max circle size and spacing based on the image dimensions and tree depth. I divide the image width into 2D parts, with D being the tree depth, having a circle diameter slightly less than that. Yes, so what you're saying is actually something very close to what we already have. And I'll go into that in just a second. However, I love the suggestion. So the difference here that you said, which I like a lot, is that you have the weight of, or the size of the circle depending on the weight of the node, which is really cool and clever. In fact, let's go ahead and just add that in there just to see what it looks like. Now, what do I want to do? Okay, what Gustrun suggested a second ago was drawing these guys out like how we do it on paper. Draw all the nodes together like this, and then add them like this. Like what we would typically do on paper here, which is fine. This would work very well. The issue here is that Checkwob, good luck with that. Could you help me out with something you got? ASM. Actually, I don't know what ASM is. Arbitrary systematic memory? That's probably not right. Yeah, that's definitely probably not right. Okay, so we could draw all the nodes like this, where we draw all the nodes starting at the same location and have the tree be drawn differently. Okay, so let's go through and let's look at this. Sorry. Just crazy stuff and no idea what's going on. Let's move this over here. Good. Now, what do we need to do? Well, let's just go ahead and modify some things. So let's do, I don't know. Let's make the GIF again. So let's make file. Let's go down to convert. Remove this. Right quit. Make. Assembly assembler source language. Oh, okay. Yeah, fair enough. Thanks, Ziffo. I'm really bad at light. I light a candle for you every day since your return. Oh. Nah. Okay. Frank, maybe disable optimizations completely. Let's do the following. Animation.gif. Okay. So this is what we currently have. That's our current animation. Let's go into Huffman visualization.cpp. It's a game creating cheats. Okay. So let's scroll down and let's see what we got. So one thing we can do is in the draw tree command, draw tree, we can actually change the size of these nodes based on where they're at, which actually could come into play pretty useful. Could be pretty useful. Gosh, I don't know what I'm saying anymore. Let's just go down here. Runtello. Okay, so what do we want? Let's go here. Let's change the size of these circles. So before I was giving them all a size of 10, let's change this to a size of 5 and multiply it by the level that we're on. So let me think. The level, let's say, divided by 7 or something like that, times... Let's see, so the highest size we want to be maybe 20. The lowest size we want to be like maybe 5. Let me think. Hey, Frank, be careful with your language. Seriously. This is not something... It's a family-friendly channel, right? We don't want that language. Good. So just be careful with that, because you could get in trouble for that. In fact, you will get in trouble for that if you keep using that language. Okay, so let's go down and let's work on it from there. So let's change the radius size. It's going to be 5 times, what do we want here? We want the maximum size, 5 times 7 divided by 20 equals 1.75. Or sure you want, yeah, that's probably too small. So let's do this. We want the maximum size to be 20. That's the maximum size. So we're going to multiply this by the following, which is going to be... Let's divide this by, or multiply it by 0.25. I'm not agitated. It's just, I don't like cursing in chat. It's one of those things that I've always kind of said. You know, this is a family-friendly channel. I realize we do a whole bunch of complicated physics and programming and stuff, and that's fine. But this channel has always been, at least in the chat, family-friendly. So, okay, where do we need to go from there? I'm trying to figure out how to dynamically size these guys, and I'm failing miserably at it. So here's what I'm going to do. I'm going to say the level that we're currently on. Let's see, if we divide that by 7, then that would be like 7 over 7, which is 1. So we want 1 over that. 20 divided by level. Let's see, 20 divided by 7. Why not? Let's try that one. We'll do 35 divided by level. Wow. Level. Okay. So let's do 35.0 and double. Oh, my bad. Double of level. I think this is fine, but hey. Write this, go over here, quit, and let's make that. And let's see what it looks like. Because maybe this will solve some of our issues. It would be reversed, the lower one would be smaller. I'm dumb. No, that's fine. You did the same thing I did. Would it be feasible to have the circles on one level, half the size of those above it? We can do that, but let me see what this looks like real quick. So I didn't change the text size, but you know, in a way this does help. Let me see. If I would have changed the text size. Okay, streamer dude. Let me see. Image. See, give them all size based on how many children there are, and offset children based on their size to make room. Let's open link. Yeah, so this is kind of what we're working on, right? Let me think. See, give them all a size based on how many children there are, and offset both children based on their size to make room. Okay, so let me think. So what you're saying is, also my name is James, for the record. You can just call me James. No reason to call me streamer dude. This is kind of what we've been trying to do, Untella, and we've been kind of screwing it up. Kozeki96, actually good debugger, like IDA, do this already. Make C-like code from EXE, which could be edited. Oh, you're talking about for Frank's thing. But it's hard work without understanding assembler and basic of programming parts, like external libraries, and what for they are, you can't do so much. That's fair enough. In fact, I'm sure there's a way. Let's see, you want to do 35 to raise the level instead? Yeah, sure, let's try that. Why not? So let's go down here, and let's say 35 divided by 2 raised to the level. So let's do power of 2 and double level. In fact, we could probably just have it level. No reason to do double in this case. Right, let's go here to make. And let's see what we got. Now, one thing to point out is we are already using this 2 raised to the double level in order to position these guys X. I did some PS1, and that was a pain. Mirage image. Okay, those are some small dots. Those are some super small dots. Okay, let me think here. It could be because we're not visualizing. Yeah, those are some real small dots. Let me think. Let's go here and let's change this 35 to like something a little bit bigger. Let's change it to 100. Okay, let me go to make. They were like, those dots didn't even exist. They were so small. Let's try it again. The final level here is 127. I'm sorry, it's 7. So that means 128, which is super small. So let's do Mirage frames. These dots are a little bit bigger, but we're not hitting the underlying issue, which is what we need to do. So let's go here. Instead of doing level, let's do level -3. Now let's do make, and let's see what happens. No, it's fine. That was great. Okay, what do we need to do? Okay, mirage animation.gif. Okay. Well, that's something. Oh, that didn't help at all. Let's change this to 35. Again, like it was before. Right, this, go over here, and let's make it. Yeah, check WAP. After that, it does this. Let me see. This is why checking lower bits. EXE. Gallo is group. Wow, I've seen some strange mix of good old C and that thing that Linus Torvald hates this. I'm sorry. Let's go here to Mirage, and let's see what we got. I don't know. I feel like... So, I actually like this difference in size. I think it's really cool. 2 level will increase very fast. When you say avoid exponential, like maybe 10 to the level or something. Yeah, let's do 10. Let's just see what happens. At this point, guys, we're just kind of playing with it. So, as I mentioned before, you guys have access to this code online. So if you need a link, let me know. I can send you guys a link again. The problem is here, I think, that each successive level can have up to twice as many nodes as the previous one. Yes, that's completely true. In fact, when we did the visualization, Mirage animation.gif, when we did... Oh, here we are. Oh, what? One second, let me take a look at this. Let me do... Oh, I'm sorry. I don't know what I'm doing with my life. Let's change this back to 2. No. 10 times will... Yeah, I know. I don't know what I was thinking. For the record, it's 7 in the morning, so come on. Cut me some slack. Of course, I say that every day, and I do this every day, so... whatever. Anyway, guys... I think this is just going to be a situation. You guys have access to the code. Let me know if you guys are, if you guys find some intuitive solutions. Outside of that, I really just need to learn how to better visualize subtrees. That's what I think we need to do. What's great about this channel is that everyone in Europe, it's like 1 o'clock in the morning or like midnight their time, so they're all incredibly tired from working all day. And then it's 5 o'clock in the morning my time, so I'm sitting here and I'm just like, just barely up, just kind of coding. Like, I literally just rolled out of bed and then started programming. So it's a situation where no one actually knows how to code because we're all just completely exhausted. But it's great. It's great. Image size for a tree that deep. Yeah, so here's what we can do. Let's change this up here. And let's change it from 35 to... Frank, come on. And now let's go and increase the size of the image. So let me go up to the very top. Go down to main. I don't know why I went to the very top to begin with. And let's change this to a size of 1920 by 1080, which is what we did before. Right, this. And actually, fair enough. Here's what I'm going to do. Just to make sure that we have all the dots of the appropriate size, let me go back down to what we had before. Also, the tree visualization algorithm is really simple. It doesn't even try to move subtrees closed when there's a child missing or something. Yeah, there's definitely more ways to do this. 1 second, let me pop down to the draw tree. And what do we have? Here's draw tree. Draw tree. Just for this particular one, let's not dynamically size these guys. Let's just say it's they're all of the same size. Right, this. And now let's go to what do we want to do? Let's just leave this here. Right, go here and let's make it, but let's first go into the make file. And let's go down to convert. Add in a comment there, and let's make that. Give it a second to do its thing. Let me see. Frank34, I got a quick question. Could you explain what your code does and how to use it with your namespace and OO design, of course? Well, the code currently is visualizing a Huffman tree. A Huffman tree is a way to create a, basically a data compressed encoding scheme, so that we can convert like a phrase. In this case, the entire phrase of Jack and Jill went up the hill to fetch a pail of water. Jack fell down, broke his crown. Jill came tumbling after. That's the phrase we're actually encoding here. I did something stupid. Yep, I did something stupid. I'm not sure why I did that. Anyway, so we encoded it into a whole bunch of different bits. It's not really like machine learning, but it is in a sense kind of there, in the same ballpark maybe. But what we're doing here is we're just doing the encoding. Machine learning is, I mean, it's open source, MIT license. You can use it. I don't know if you can really use it very well. Are we elite yet? Apparently not. It took me a while to read that. I screwed this up. Let me go down here. Let me go down to where we're actually drawing each of the individual dots. Here. And let me change this around. What am I doing? I don't know what I'm doing. Ah, crap. Why do I never know what I'm doing? Let's go here. Let's all just give them a standard size so we don't have to worry about it. And let's give that size to be, I don't know, I'll say 35. Right, this, go over here, and let's make it one more time, and then we'll look at the images. This is answering the question. This is Linux. Nobody will be able to use it. I mean, you should be able to use it. Pretty sure. I'd be surprised. All you have to do is run the make command, and the make command should do it for you. If you have Cairo installed, that is something you have to have installed. You have to have Cairo installed. Okay, thanks, Untillo. Sorry about that. Open link. Let's see what we got here. Get node size, node, int left is node left. Get node size, node left, 0. Return left, right. Float left, offset. Get node size divided by 2.0 float. Okay, so we get node size, int left, node left. 1 second. Struct node, and you make pointers for node. There's a node already defined before. You can compile this code on Windows if you code it on Linux. You can totally compile certain code on Windows if you compile it on Linux. Let me go here. Here's the image. This is what I was trying to show before, in that increasing the size, the resolution size does help a little bit if we have a static sized dot. However, you have to. There are still some locations that are not fixed by this. So let's move down. Like, for example, these guys are overlapping, and these guys are overlapping over here. Okay, it relates this from before. Image. Yeah, exactly. I think this is the image that you said before. Let's see, what do we have? Open link. Yeah, same image. It actually compiled this whole thing on Windows using min.gw. Okay, good. Thanks, Gustorn. It finds the size requirement of a child, then you can offset it by the child that amount. Yes, okay. We can do that. Gothic Death Eater. All you have to do is compile it under Windows. You sure, Gustorn? I tried and it failed. Missing Cairo? Probably. Can't find the linker symbol. Yeah. Did I put it in the README? I don't think I have a README for this directory. Let me see. Write and quit. ls. No, I don't have a README. Let me go into the make file. So the make file is right here. Let me just scroll a little bit. The make file is right here. And yes, you do need Cairo to compile this. Frank, I think it might help if you actually paste it. Yeah, exactly what Zadistan said. Okay, guys, so here's what I'm going to do. Untello, you gave a good idea. There's actually quite a few good ideas that have come about via this discussion. But at the same time, I think I need to go through and just think about how we want to do this. So there's a whole bunch of good ways to draw subtrees, a whole bunch of other things in there. ANSI C89 is totally compiled standard for all systems. Best way to code. Sure. We've been using C++ 11 for this. No, we could be using C, but again, C++ 11 has a lot of features. I have not yet moved to 14. In fact, it took me almost like 3 or 4 months to move to C++ 11. So I don't know. I'm kind of slow with this kind of stuff. But I wasn't even planning to be born in '89. Just use Windows Linux. Use Windows Linux is only for hacking and not for coding. Mad physics. Why would I go back in time? Mad machine learning physics. Okay, so here's the thing. That could be true, Gallows Group. In fact, you're probably true. I think there's a lot of computing clusters out there where I'd believe you. I believe that they wouldn't have C++ 11 installed. In fact, I know that's true because at my old university, I had to figure out how to manually compile G++ or the GCC for C++11 for it to work out. C++ if you know what you're doing. Yeah, I agree. Then everyone should learn assembly. Like that, errors would be avoided. Okay, let me go to Huffman Visualization. Sorry, Huffman Visualization.cbp, and let's lower the resolution again and fix a couple things up. So what are we doing? Let's go here. I'm gonna bring the resolution back down so it makes it a little bit easier and we can make a good animation. 300. I don't think Gustorn does any coding in Java. I think he's fine without Java. Okay, so let's go up here. What was I doing? I was doing this. Here. So let's give these guys a non-static size again. Gustorn totally took offense to that one. Okay, now let's just make it. And we're going to look at the code that we currently have. Okay, so let's go into the last image here. Let's scroll down. Okay, well, I'm clearly doing something stupid here. Let's do level -4. Over here, right? Actually, I think I need to go the other way, don't I? Level -2. And then let's do make. Okay, languages like Java are a little rubber padded playground, whereas C is like a kitchen full of knives where you're asked to kindly not kill yourself, and C++ is that same kitchen, but every surface is knives. Could be true. I've got a friend who's working on, you know, basically safety features for C++. His research is in that, and that's the thing. There's a whole bunch of cool things there. Anyway, guys, it's 7:06 in the morning. You guys have access to the code, so feel free to mess around with it, do whatever you want with it. That's perfectly fine. We tried a whole bunch of different visualization schemes. We still have a little bit left to do. Now, Untello did give a suggestion that I'll look into this afternoon. Unfortunately, I'm kind of fried right now, so I can't really think very clearly. So what I'm going to do is I'm going to go ahead and end the stream here. Assembly is, let me see, the same kitchen where every molecule in the air is nice. That's totally true. Otsukare-sama, yes, exactly that. So today is going to be, I'm going to go ahead and end today here, and tomorrow we'll continue with the visualization schemes. I apologize for taking so long with this visualization. I realize it might be a little bit frustrating for some people because I'm doing this the whole time, but that's okay. That's how it happens sometimes. I need to just sit down and read some more today and figure out if we can figure this out. There's a lot left to do there. Gothic Death Eater, the more kanji you put in, the less I'm able to read the Japanese. I apologize for that. Karuna o... don't know. Sorry about that. Anyway, guys, that's it for today. If you're new here, I'll take a look at this in just a second. Let me see, what do we have? Can we watch it without, let's see, Perl, Python. Okay, good. Java C. Okay, Kyotsukareru naomai. I don't know. I'm really bad. I'm sorry. I'm really sorry. My Japanese is awful, even though I live in Japan. Okay, so that's going to be it for the day. If you haven't been here before, feel free to check out my YouTube channel where I also post a whole bunch of cool stuff. Obviously, if you're interested, feel free to subscribe there too. You know, that's just the way it goes. Also, of course, following on Twitch, I'll be live tomorrow at 5 to 7 o'clock a.m. Japanese Standard Time as every day. Yes, I do live in Japan. I work at the Okinawa Institute of Science and Technology in Okinawa, Japan. Anyway, guys, that's going to be it for the day. Thanks so much for coming in and taking part in the discussion. Have a great day, night, afternoon, morning, evening, whatever time it happens to be your time. And I will see you around next time for the next episode of Simuleos, where hopefully we figure out how to draw this tree. That's about how far we've gotten. And then we'll go from there. Zadiston, watashi no hoba Kurafuto wa. Oh my gosh, why does everyone know more Japanese than I do? Gosh darn it. Okay guys, that's about it. So again, I'm going to close the stream right about now. Thanks again for watching, and I will see you next time. Bye, guys. See you around.